All right, here we go. Review key video. For the first couple, it's really helpful to have like some simple examples down that you can apply. Like x squared times x cubed. What is that? Some people think it's x to the fifth, some people think it's x to the sixth. Well, I always say when in doubt, with a situation like this, you could write it out. I got x times x and then x. How many x's do I have multiplied together? It's 5. Versus like maybe I have x to the fifth over x squared, or I have x squared over x to the fifth. Here's 2 examples that are important to know. Well, every x over x ends up, so we realize we can add. That's what I kind of wanted to get to. This is like 2 plus 3. Every x over x is 1. So like if I write out all these x's, 1, 2, 3, 4, 5 x's over 2 x's, whenever I have an x over x, that's just a 1. What happens is I end up with 3 x's on the top and just like nothing, or a 1 in the bottom. So you can write this as x cubed over 1, you can write this as just x cubed. What you realize is like you subtracted these 2 numbers, 5 minus 2. Now if we do it here, this is xx, xx. Boom, cancel, cancel, cancel. I'm 3 x's in the denominator. So since I have more in the denominator, I end up with these 3 left over. And notice like we do subtract a 5 minus 2 to get this 3, but we realize that wherever we have more, that's where we're going to have some leftover x's. There's other ways to do it where you deal with negative exponents, but we won't worry about that. And then the last one, the classic one we'll use frequently, a power to a power. Well, again, you can write this out. This is x squared 3 times. That's x squared, x squared, x squared. That's 6 x's. What do you get? This number is a product of the powers. Okay? So now that we have fractional exponents, we can use these as examples. So here, x to the negative 2/9 and x to the negative 1/9. Well, if I'm multiplying, you can see I can just add the exponents together. Here, I added 2 and 3. Here, I'll add negative 2/9 to negative 1/9. Some of you are intimidated by fractions. It's okay. You can use your calculator. You can use the alpha F1 if you want to. I don't think it's necessary. You can always just use division as a fraction. And we get that, and remember math, enter, turn things into fractions if you want to. So this is x to the negative 1/3 because I added the 2 things together. So it's a really negative 3/9, and this turns into negative 1/3. Now, we have to remember, and I showed you in the notes, if I take a number to a negative power, it's the same as the reciprocal or the flipped number to the positive power. And this is the answer that we would be looking for, something like this or something like this. I actually won't care for my students for a question like this. Okay, we have x to the 4/3 and x to the 2/3. I'm going to look at this situation. Well, I have more in the numerator. 4/3 is greater than 2/3. And what I ended up doing is subtracting the 2 numbers. Here, 5 minus 2, 3. Okay, so I have x cubed. Here, I'm going to take 4/3 and subtract 2/3. Again, you can use your calculator. 4/3. Let me just use the alpha F1 if you want to see that. 4/3. And then minus 2/3. I don't know why. I guess you get your answers in terms of fractions. So we end up with x to 2/3 over 1, okay? Or just x to the 2/3. Either is correct. Multiplying things. I got 2, I got 3 x's, I got 3, I got 2 x's. Well, I'll multiply my numbers. 2 times 3 is 6. But I'm not going to multiply these powers because, just like we showed, 3 x's, 2 x's, I get 5 x's. I'm not going to get 6 x's. I got 6 for a number. 6 is the 2 times 3. And then this is x cubed and x squared. Okay, we have a power to a power. In this situation, I can write it out. It's 4x cubed times 4x cubed. Okay, well, You could also have distributed the power and say this is 4 being squared and then x cubed being squared. Either way, you're going to get 16x to the 6th. And that's pretty much what we do here. We'll distribute this 1/2 power. It's a square root. So I have 16 to the 1/2 power, and then x to the 2/3 to the 1/2. Now, if you're not sure about 16 to the 1/2, you can always type it into your calculator, 16 to the 1/2. Now, be careful. If you have an older operating system, you might want to use parentheses around this power. If you end up seeing like a caret instead of seeing it go up to the power. So maybe use parentheses, and we see that it's just the square root of 16. It's just positive 4. Now here, 2/3 to the 1/2, power to a power. What do? We multiply the two numbers, right? This is 3 times 2 to gives me 6. I'm going to take 2/3 and multiply by 1/2. 2/3 times 1/2. I get 1/3. And that's my answer. You can write it like this, or you can write it as 4 times the cubed root of x. A power to a power. Again, multiply the powers. We use this example up here. Power to a power, multiply the two powers. 1/4 times 4/3. Again, I get 1/3. How do I know that's 1/3? You can math enter if you want to. You can just remember, 0.3 repeated is 1/3. All right, so that's that. Now, this next one seems tricky. I got x cubed, and then what I would recommend is turning this to a 1/2 power. Now let's go back and think. What do I do when I'm dividing? I end up subtracting the powers, and wherever I have more, that's where they end up. So I'm going to want to subtract these powers. Now, it doesn't seem like an example that we've done before because we've got a whole number and a fraction, but that's okay. You could subtract a 1/2 from 3. You get 2.5. Now, that's the same as 5/2. So more in the numerator. We have this over 1, or just that. All right. You can leave it like that, or we can write it as the square root of x to the 5th, or we could write it as square root of x to the 5th. Here, power to a power, just like the other ones, you can multiply 3/4 and 1/3. You get 1/4. You can math enter out of that. We don't like decimal. We prefer fraction powers. So this is x to the 1/4, or the 4th root of x. It's not 4 times the root, it's 4th root of. Okay, and now we start simplifying things like 54, square root. Now, all of these, this is just a 1/2 power. We're going to be square rooting all of these. Now, this might be different than what your teacher teaches you or what you've seen in the past, but this is what I would do. I'd probably start by understanding that it's a 1/2 power. That way, when I take a power to a power, I can multiply. So 4 times 1/2, I got 2. 7 times 1/2, I end up with 7/2, or 3.5. We'll talk about that in a second, what we can write. Probably actually for my students, I would accept it like this, but I'd expect you to do one extra step to show me you know what's going on. And it's actually something that you'll have to do maybe on like an SAT. So we'll talk about that. Now 54 is not a perfect square, but I know 9 is a perfect square, and that goes in 6 times. So root 9 times root 6 is root 54. I'm like splitting this up and splitting up the powers. The square root of 9 is 3. The square root of 6 is not a number. It's a decimal. So I'm going to write this as 3 root 6. Now 7/2, 3.5. That is y cubed with another half y. Or that is y cubed root y. And this is what we would look for an answer. This is one way. Or to make it look nice, we can combine your numbers that are not being rooted, put them next to each other, then take the numbers that are being rooted and put it under one root. So both of these would be accepted for an answer, and I would expect my students to simplify y to the 7/2 in a situation like this to be y cubed root y. All right, next ones, square root of 9, x to the 5th to the 1/2, y to the 7th to the 1/2. I got 3. I got x to the 2.5, that's 5.5. I got y to the 7/2. We just did that. So 2.5 x squared with another x to the 1/2. 3.5, 3 and another half. And you can keep it like that, or switch it with that. Okay, cubed root has a 1/3 power. Now, if you're intimidated, maybe use this 1/3 power instead of use this cubed root. It'll definitely help when I understand what's going on with x to the 12th to the 1/3. Power to a power, multiply the powers. Multiply 12 and 1/3. Well, it's 12 divided by 3. That's 4. I'm not sure about negative 27 to the 1/3. Type it in your calculator, you get negative 3. Same deal here. X to the 12th to the 1/3, 64 to the 1/3. You can like distribute that power. A bunch of things too. I guess we could probably show that, like 3x squared cubed would be 3x squared, 3x squared, 3x squared. That ends up being 3 cubed and x squared cubed. So 27, x to the 6, that's a good example to have, just to remember. So that's what I'm doing here. I'm like distributing the power to everything. 12 over 1/3 is 4. Cube root of 64 is 4. You can type that into your calculator as well. 64 to the 1/3. 4. All right. Some more. We got these. Square root of 16 is 4. 8 times 1/2 is 4. 12 times 1/2 is 6. Boom. I don't have to simplify. It's no and a halves. Here, root 25 is 5. I got x cubed to the 1/2. I got y to the 6th to the 1/2. This is 5. This is x to the 1.5. This is y cubed. So 1.5, I have 1.5 x's. And this is 5xy cubed root x. Cubed root of 24, I don't know what it is. But I know a perfect cube is 8. And that 8 times 3 gives me 24. Now, you don't know what the cube root of 3 is. So you're just going to leave it as the cube root of 3. But the cube root of 8 is 2, right? 2 times 2 times 2 is 8. So I'm going to simplify this to be 2 and then leave the cube root of 3. Now here, a to the 15th will be taken to the cube root. That's to the 1/3 power. B to the 9th to the 1/3. Multiply the powers. 15 times a 1/3. You can type it into your calculator. You get 5. 9 times a 3rd, you get 3. Just leave it like that. Okay. 3/2. This could be written as x cubed to the 1/2, or it could be written as x to the 1/2 cubed, which means we can write it as the square root of x cubed or the square root of x cubed. These would be the radical form answers. Either is acceptable. Here, x to the 2/3. Well, 2 times 1/3 is 2/3, or 1/3 times 2 is 2/3. So that means I can write this as x squared, and then the 1/3 is a cube root, or I can write this as cube root squared. Either is correct. 7/3, x to the 7 to the 1/3, or 1/3 times 7 gives us 7/3, which means this is a cubed root of x to the 7th. That's how I'd write it here. And I would write it like this, cubed root of x to the 7th. Both are correct. All right, fractional powers. Well, I would recommend doing this always. We know that a square root is a 1/2 power. So if this is a 1/2 power, 1/2 times 3, 3/2. You can do that in your calculator if you're uncomfortable with 3 times 1/2. It's 3/1 times 1/2. 3 times 1/2. I mean, I'll show you if I have to. I hope I don't have to. Math, enter. There's my fraction, 3/2. Okay. This is x to the 5th to the 1/3. Multiply those together, you get 5/3. This is x squared to the 1/3. A cube root is a 1/3 power. This would be x to the 2/3. Okay, and these would be my answers, this one, and this one. All right, graphs. Man, if we don't know how to graph equations, that's concerning. Square root. You have a square root button. You also understand that you have a 1/2 power. Both of these graphs are the same, the square root of x and x to the 1/2. What points do you have? You don't have 2, 4. You have 4. The square root of 4 is 2. 4, 2. The square root of 1 is 1. 0, 0. Square root of 9, 3. Okay, so these are the points on the square root of x function. The domain, are x is greater than or equal to 0. You can write it like this. You can write it like this. You'd include 0. We want to include infinity. The range are all the y's bigger than 0. We will continue going on to infinity, so including 0 going to infinity. Either of these answers are acceptable. Probably these are easier in my opinion for some students. All my x's are bigger than 0, all my y's are bigger than 0. Cube root, how am I going to graph that? Well, in my calculator, I don't see a cube root button on this front. So I'm going to use a fractional power. There's the cube root of x. I'm not writing it as 3 root. This is not correct. This is not the same graph as this, the cubed root. So don't do this. It's wrong. That's 3 times the square root of x. Okay, some points on the cubed root of x are like 1, 1, sure. But we can also have negative values. Negative 1, 1, 0, 0. The cubed root of 8 is 2. I got to go all the way to 8. I think this is 8, 2. And then negative 8, negative 2. And this is what the graph of the cubed root of x would look like. And though it'll take me a while to get bigger and bigger y's and bigger negative y's, we actually can plug in any value and we would get out any value. So cube root graphs are easy in terms of domain and range. Now, man, we're not sure about the transformation. We're not sure what's going on here. Goodness gracious, we should graph. We should always graph. Make sure it's exactly how it looks. Make sure your square root, your x plus 1 is under your square root. And then the 2 is outside. You got to click on the right button to get outside the square root. You realize if you can compare this to the square root of x, that we've shifted to the left one and down 2. Left 1, down 2. So I'm just going to do a quick sketch of that. I'm not going to be specific. The domain now are all my x's that are bigger than or equal to negative 1. I've shifted everything to the left 1. So subtract from 0, 1. So that's going to be from negative 1, including negative 1 to infinity, instead of from 0 to infinity, which was my previous one. My y's now are all bigger than negative 2. I subtracted 2 from my y's. I shifted down 2, so I take my y's from the root x, subtract 2, and I'm going from negative 2 to infinity. I can see, it's obvious that I'm going left 1, it's a shift, then down 2. This guy, type it in, negative. Don't put a subtraction symbol. If you put a subtraction symbol, watch what will happen. Subtraction x minus 3 plus 5. My calculator says, no. Syntax. What is a syntax error? It means like it doesn't understand what you typed in. Don't put subtraction, put negative. Now we see we shifted to the right 3, I went up 5, and then I flipped. So I flipped over like an x-axis. So now up 5, over to the right 3, I'm right around here. I'm going down this way. Don't worry in my class about specifics with that. My domain is all my x's, okay, so I have all my x's that are now bigger than or equal to 3. All right, so that's 3 to infinity. But my range is not all the values bigger than 5, it's all the values less than 5. All of my graph points have y values less than or equal to 5. So I flipped my y's because of this negative. Now I have to go from negative infinity to 5. What's the transformation? Okay, right 3, up 5. That's my shift. But then I have a vertical reflection. A reflection of my y's. I'm doing this outside. Remember, outside the function will affect the y's. Inside the function will affect the x's. This example right here and these examples right here are going to help us when we start writing transformations. Okay. So now we got the cubed root. Well, we already graphed the cube root function. Remember, we have to use a 1/3 power. So here, be careful. Put in parentheses all the stuff that is in the 1/3 power. Subtract 1. I could add -1. Okay, so what happened? Well, it looks like I went down. Since this negative is actually inside, I'm actually reflecting all of my x's. Now, a reflection of your x's, would that be different than a reflection of your y's? You got to think about that. So if we have this, and if I reflect my y's, it's boom there, and I reflect my x's, okay, yep, it's actually going to be the same thing. So what we find is that this negative could be inside or outside, and it doesn't really matter. So in terms of our transformation, we'll talk about it. Just do a sketch. It doesn't have to be perfect. The domain is still all reals and range is all reals. If you have a cube root, man, isn't that easy? That's nice and easy. Transformation is down 1. And then I would say, since it's inside, you would say you're reflecting your x's. So reflection horizontally, but it ends up, you could also say vertically, because the reflection will look the exact same, either vertical or horizontal, with this graph. Yep. This, I got stuff inside, I got stuff outside. Let's be careful when I'm typing it in. In parentheses, x plus 2 to the 1/3 power. I forgot to add in a 2 before this. Watch a second, insert. Boom, I've just inserted a 2. So if you've never inserted things before, that's how you do it. Second insert, and then you can kind of add stuff. I'm subtracting 1. I know that I'm going to shift left 2, I'm going to go down 1, and this is going to be a vertical stretch of 2. There we are. So left 2, down 1. Here's like my epicenter kind of. It's a little bit stretched. I'm not going to be specific. It doesn't have to be perfect. Okay. And that's important, that this is a vertical stretch. We are stretching the y's because we're outside the function. This would not be a horizontal stretch. That'd be a vertical shrink. Okay. We got the cubed root function. I want to shrink it by 1/2 and go 2 units up. So g of x has to be the cubed root of x. Since I'm doing things vertically, up, vertical, I'm all outside. So the 1/2 is going to be multiplied to do my vertical stretch or shrink. This is going to be a shrink, so I don't have to change anything. 2 up, add 2. Reflection over the y-axis. The y-axis is the horizontal reflection. 3 units left. So now we're talking about all stuff inside my function. I'm talking about the function the square root of x. So I got to do inside. So I am translating 3 things to the left. Well, I think this might be tougher than we think it is. And then if I put a negative, does that work out? Yeah. No. See, look, I went 3 units to the right. So it's almost like I have to do the negative and then the x plus 3 like this. I wonder if my other key is correct. So it should be, and this is why we graph to check. That's 3 units to the left. And you're like, but why, Mr. Messer? Isn't this like isn't this opposite? Don't we need a plus? Yeah, it's a little trickier with this reflection. Not a great question. Probably on your test, you probably see this reflection across the x-axis. So an x-axis, that's probably when you're going to see, your y's flipping, and when your y's flip, you got that negative on the outside and the x plus 3, and you'll see that. I wouldn't give you that question on the test because it would confuse you. I don't want to confuse people. Now we see this will shift us left 3 and reflect over the y-axis. Funny how that is. Up to left 3. So left 3 is an x, opposite. So this is x plus 3 inside my square root. And then up to, I'm going to add 2. Whenever it comes back, there it is. I'm going to add 2 to the outside. Outside is the y's. It's normal. Here, I'm reflecting over the x-axis. The x-axis changes my y's. I'm shrunk by a factor of 1/4. That's a vertical shrink, so that means I need a 1/4 in front of this and a negative. And I'm going to the right 2 units. The right is an x, so we're going inside, and it's opposite of what we would think. And obviously, I would graph these to check. Okay? All right, moving on to solving equations. We have 2 pages of this. I'll try to do this in the next 15 minutes. I think I can. Here's the key. Isolate your power. Instead of using the root, I like to write it as a 1/2 power. Because now I can see that if I take both sides to the power of 2, the 2 times the 1/2 gives me 1. It's a reciprocal power, and it will undo what the 1/2, what the square root is doing. So you square a square root to undo a square root. I will then finish by adding 3, and I get 19. Here, just like I would solve the equation 6x plus 3 equals 27 by first subtracting the 3, I'm undoing order of operations, and then I would divide by 6. I'm going to do the same thing with this. I can't get this 2 out of here because it's inside this power, but I can isolate the power so that I can get rid of the power. I'm going to isolate the square root by getting rid of the 3, getting rid of the 6. Now I have x plus 2 to the 1/2 equals 4. Take both sides and square them. Because the 1/2 squared gives us a power of 1. A power of 1 is just x plus 2. Then 4 squared is 16. I'd finish off by subtracting 2. If you have just square roots on both sides, you can also just ignore the square roots because watch, you would take both sides to the power of 2. You'd square both sides, and all of a sudden you just have whatever's inside. So you actually don't have to show this step in the future. In the future, you can just be like, well, I can just ignore the square roots and figure out the numbers that go inside them. 3x minus 5 equals x plus 9. Maybe you subtract x from both sides. Maybe you add 5 to both sides. Maybe you do other things. You can do whatever you want so long as you get, after dividing, x is 7. Okay? Then we can always check, plug it back in. 21 minus 5. Okay, so that's 16. 7 plus 9, 16. Square root of 16, 4, 4. Okay, we're good. Something like this. Isolate the square root. Divide by the 4. Maybe don't write it as the square root. Maybe write it as x to the 1/2. Maybe this equals 5. Square both sides. 1/2 to the second power. 1/2 times 2, that's 1. 5 squared, 25. Fractional powers, the same deal. Isolate the power and add 38. Okay, so I got 3x to the 2/3 equals 48. I'm going to divide by 3. I got x to the 2/3 equals 48 divided by 3. You're probably using your calculator for this, right? 16. Okay, now what do I do? Well, to undo this 2/3, so it's just x to the first power, we will take both sides to the reciprocal power, because 2/3 times the reciprocal 1 over, or 3/2, is just 1. Okay? Just flip a fraction or flip a number like 6. Its reciprocal is 1/6. 1/2, its reciprocal is 2. 1/3, its reciprocal is 3. Because this gone, just x to the first. Now all I have to do is figure out what 16 to the 3/2 is. 16 to the 3/2. Boom, 64. Done. That's what x equals. X equals 64. I don't need this first. X to the first. I don't need that. It's just x. Okay, divide by 2 would be my first step. I got 3x plus 5 to the 3/2 equals 8. I got to get rid of this 3/2. What should I do? Take both sides to the 2/3 power. I get 3x plus 5 equals 8 to the 2/3. What's that? I don't know. Type it in your calculator. 8 to the 2/3 is 4. Look at that. That's nice. Now I solve. Subtract 5. Isolate x. Divide by 3. My answer is a fraction. Don't be afraid. This is correct. This is good. Okay. Next one. A cube root. A cube. Don't worry. I don't think we had any cubes in our notes. So sorry, teachers who didn't show that. I think I showed an example in my class. But I think we can handle it. If we can handle, 1/3 powers, we can handle any powers. This is a 1/3 power. How do I get rid of this 1/3 power? Cube. Because 3 times a third is 1. So this is x plus 10. To the first, gone. 2 cubed, 8. Subtract 10. Subtract 10. X is negative 2. Look at that. Isolate the cube. Let's add 16 to both sides. Right? We're going to add first, then divide, just like I would when solving an equation. Reverse order of operations. I got 30. And divide by 6 now. I got 25 to the 1/3. I can't get rid of this 25. It's in this power. Got to get rid of the power first. How do I get rid of that? Cube both sides. Take both sides to the 3rd power. A lot of you are like, oh, multiply both sides by 3. No. It's taking both sides to the 3rd power. But since it's an equation, if we do it to both sides, the equation stays balanced. So this is fine. This gives me 25x equals 125. I then divide. Just make sure 5 cubed. Okay, good. Divided by 25. 5. Sweet. Okay, what about a cube? What do I do with a cube? 1/3 power, right? 1/3 power will undo what's going on. I got x cubed equals 189. Gosh, what's 189 divided by 7? No way does that divide evenly. Am I right? Am I right? Am I right? Oh my goodness, 27. What do I do? What do I do? I could think. I could literally just think. What number times itself 3 times gives me 27? 3. Maybe you don't know that. Maybe you're not thinking. Take both sides to the 1/3 power. I don't know what 27 to 1/3 is. Yes, you do. You have a calculator. Use it. 3. Oh, no. a third power, what do? Take both sides to the 1/3 power. I don't know what 8 to the 1/3 is. Type it into your calculator. You get 2, subtract 4, -2, right? Subtract 4, 2 minus 4, 2 minus 4, 2 plus -4, -2. Okay, I got an isolated square root, but what happens if I want to get rid of it? I got to square both sides, but here's the problem. If I square the right side, I'm not just going to get x squared minus 49. No, we know that's not correct because we know that x minus 7 times x minus 7 does not give us x squared minus 49. It gives us x squared. Okay, I got a -7x. I got another -7x. Then I got another 49. And this is how we realize when we factor, we're looking for two numbers that add to get -14 and multiply to get 49. Here are my two numbers adding together, and then here are my two numbers being multiplied together. Okay, so that's how we factor. That's how we go backwards distribution. Over here, I have 2x minus 14. Oh, what do? Okay, x squareds and x's. This is a quadratic. This is a quadratic equation. If you just write that, and you realize you got to get everything onto one side. I'm going to have to subtract 2x. I'm going to have to add 14. So that I get 0. Quadratics love being set equal to 0 because then we do things like the quadratic formula. Or we could do my favorite thing, factoring. Just like, okay, let's see. What do we do? Okay, -7, add to get -14. Okay, -7 times -7, 49. That's what we need. I need to turn this into something that looks like this. I got to figure out the numbers that go here and here, and I'm hoping that there are two numbers that multiply to get 63 and add to get 16. It's probably two negative numbers. I'm thinking 63 is 9 and 7. Let's see. 9 times 7, 9 plus 7. Boom! But they've got to be negative. Giving me answers of 9 and 7. Great. That's what I think are the answers to both. I should probably check. There are situations where you can have extraneous solutions. If you look, first of all, if I plug in 9, 9 minus 7 is 2. Okay. 9 times 2 is 18, minus 14 is 4. So this is the square root of 4, that's 2. Okay, so 9's good. 7's also good because I'd get 0 and 0. If you graphed to check, and remember we learned this, and we can do this for any equation that we've done. So when you're doing your tests, like I would advise you to go back and check all of your answers. We can see it looks like it intersects here and here. Now my calculator might not say that there's an intersection. At 0. Yeah, it just goes to this one at 9, but there is one. You should know, you should be able to check and see. All right, here's another one. We'll square both sides. I think I can finish this in time. I get x plus 22. And this is, okay, well, let's see. It's x plus 2, x plus 2. What is that? Okay, that's x times x, 2 times x, the other 2 times x, and then 2 times 2. So these two numbers add together. So I get x squared plus 4x plus 4. Fantastic. It's a quadratic equation. X's and x's. Get everything onto one side. Subtract x, subtract 22. Subtract x, subtract 22. This gives me x squared plus 3x. This is minus 18. 4 minus 22. Make sure you're doing it in that order or adding the opposite so that you get a negative value. Okay, now, we realize through this process how the two numbers that add give us the middle number, 2x, 2x. They multiply to give us that final number. I'm going to do x plus something times x plus something, hopefully. If I can't do this, what do I have to do? Complete the square, quadratic formula, the tough stuff. But boy, do we hope that this works out. Let's see. Negative 18 are the two numbers that must be multiplied to get, and positive 3. Well, let's think positive 6, negative 3, doesn't that work? It does work. So that means my answers are going to be negative 6 because negative 6 plugged in gives us 0 on the right side, And 3, because when you plug in 3, you get 0. 0 times anything is 0. See, we have a 0 on this left side. It's equal to 0. We're solving an equation. When does the right side equal 0? Here and here. Now, we go back and check. We can either graph or plug in, and we find that -6 is definitely what we consider an extraneous solution. So when we graph and kind of see, we notice that at -6, I'm definitely not going to be intersecting. Okay, my graph is all the way up here. But I see that at 3, I do. So you need to show -6 as being found, and then you need to label this as, cross it off. We call this an extraneous solution. It's not a true solution, and it happens because of squaring the x, getting the x squared. All right, that's the video. I hope we respond well to it. Good luck out there.